Today we're going to look at section 4.6, complex numbers. Our objectives are to be able to write a complex number in standard form, to simplify imaginary numbers, to rationalize the denominator with imaginary numbers, to graph a complex number on the complex plane, and to find the absolute value of a complex number. So first, what is an imaginary number? For us, it is defined as, we use the letter I, as equal to the square root of -1. If you remember back from algebra, when you tried to take the square root of a negative number, your teacher might have said, well, this isn't possible. Well, it is possible, but for what your knowledge was for math, it wasn't at that time, because you guys were only dealing with real numbers. The square root of a negative number we consider imaginary. So what is a complex number then? Well, a complex number is just a combination of a real number with an imaginary component. So for example, A would be our real number, B is a real number, and an I is the imaginary part. So for example, I could have 3 plus 5i, where A and B are real numbers, but I is our imaginary part. So when does this come into play? Well, when we're solving for x in this example, I'm going to take first, I'm going to subtract 11, so that's going to give me negative 48. Then divide by 2. Everything so far is exactly what you guys have done before, equals negative 24. So we get x squared equals negative 24. But now we know to get x by itself, we have to take the square root of both sides, and this is where the problem comes in. The square root of x squared is x. And now here I should get plus or minus the square root of negative 24. So really, this is just plus or minus the square root of negative 1 times the square root of 24. Well, we know the square root of negative 1 is just I. So this is I times the square root of 24. Well, square root of 24 we can break down. Hopefully you remember that from our last lesson. 24 is just 4 times 6, so I get plus or minus 2i times the square root of 6. So the reason I know my answer is imaginary is because at some point I was taking the square root of a negative number. Every other part is exactly the same. What we can do from this step is just take out the negative, make it an I, and then deal with the 24 like normal. Let's look at another example. Here I have x squareds on both sides. It doesn't matter what side of the equation you move them to. I'm going to choose to move them to the right. So I'm going to add 9x squared to both sides, which is going to give me a 12x squared plus 7 equals 4. I'm then going to subtract 7 from both sides to get a negative 3. I'm going to divide both sides by 12, which gives me a negative 3 over 12. And I'm going to choose to simplify that to negative 1/4. And now here's where I have to take the square root of both sides. Okay, I'm just going to do my work up here. I'm now going to get x is equal to plus or minus the square root of a negative 1/4. And you can look at this a couple of different ways. First thing I always like to do is I always like to just take out the I, okay? So that way I don't have to worry about the imaginary component. Then deal with the rest. Okay. What is the square root of 1? Well, it's 1. What's the square root of 4? It's 2. And then I just add in the I. Okay, it's like any other variable, we always like to put our numbers in front. I wouldn't write I 1/2. It's the same thing as 2x. We write 2x, not x2. Because 1/4 is a perfect square, I get exactly 1/2. Again, it's still plus or minus with my imaginary component. These are considered just pure imaginary answers, this one and the one before. This isn't considered a complex number. It's actually a pure imaginary. Well, it's a type of complex, but because there's no real component attached to it. So what happens if we don't just have an I in our problem? Can we have higher powers? We can. So if I remember, I is equal to square root of negative 1. Well, what if I had I squared? Well, that just means I had the square root of negative 1 squared. Well, what is the square root of negative 1? Just negative 1. What if I had... Sorry about the bell there. What if I had I cubed? Okay. Well, that's just an I squared times an I. Well, I already found out that I squared is negative 1, so this is negative 1I. Whenever we simplify imaginary numbers, we never want to have an I with an exponent greater than 1. Let's try another one. What if I have I to the 4th? Well, I could break that down to I squared and I squared. I squared is a very powerful one to know. This is probably the most important, besides obviously the first. because you can break everything down into I squareds. I squared is negative 1. Well, if I have negative 1 times negative 1, I get a positive 1. So let's try one more. I to the fifth. Well, I to the fifth I could break down to I to the fourth times I. Well, we just found out that I to the fourth is 1, so this is 1 times I, which is just I. And so we start to repeat. For example, if I did I to the sixth, that's I to the fourth times I squared. Well, I to the fourth is 1, I squared is negative 1, so I get a negative 1. If I notice, I is what I started with, negative 1 is next, so if you actually did the work for I to the seventh power, I'd get negative 1I. If I did the work for I to the eighth, I would actually just get 1, and the cycle continues. But we're going to try simplifying, and if you just remember that I squared is equal to negative 1, it's going to be very easy to simplify a lot of our problems. So we're going to simplify 7 minus 3i plus 8 plus 10i. Now, look at the i's like they're x's, y's, a's, b, just any other variable until the very end. So I don't really need the parenthesis here because there's an imaginary 1, so I'm going to rewrite it without a parenthesis. I don't need the parenthesis here because I'm not distributing anything. So now I'm going to combine like terms. We always do the real component first. So 7 plus 8 is 15. I have a negative 3i and a positive 10i, so I get a plus 7i. This is my real, my a plus bi for my complex number. And again, it will be marked wrong if it's not written in this form, a plus bi, because I'm asking you to put it in standard form. I is to the first power, so I don't have any more work to do. Let's try this one. Here I'm going to have to distribute first. I'm going to get negative 20 plus 8i. I'm going to distribute minus 9 plus I. Again, we do the real component first, so I get negative 29 plus 9i. It's in standard form, and I'm done. All right, so now I'm going to get a little bit more because now I already see I have an I squared, so I know it's going to be a little bit more work. So if I go through here, I get a negative 4 plus 12i. Okay, now I'm going to distribute a negative I, so minus 4i. A negative I times a negative I is just like negative x times negative x is going to be a positive I squared plus 6i squared. So we always put our real component first, so the only thing I have is a negative 4. Then let's deal with the i's, so 12 minus 4 is positive 8i. And then we have my I squareds, plus 7i squared. Now I'm okay with having i's, and I'm okay with having a negative 4, but this I squared I'm not happy with. Remember, I squared is just negative 1. So this is 7 times negative 1, which is negative 7. Well, now if I combine like terms, I have negative 11 plus 8i. This is in my form, a plus bi. So there's my standard form. I have a real component and an imaginary component that has an exponent no greater than 1. Let's try one more. So this one, a lot of people make a mistake on this one because they think they're going to distribute the 10i to everything. You only distribute it to the first parenthesis. Okay, so I'm going to do 20i minus 20i squared. But remember, this is still being multiplied by 5 plus I, so I have to use parentheses. So there's lots of little places that students make mistakes here. So now you have a couple of choices. I could distribute, but I could make my life a little bit easier by cleaning up the I squared first. So I know this is 20i. If I know I squared is negative 1. This is negative 20 times negative 1, which is a positive 20. And now 5 plus I. So it helps me from keeping my I exponents getting too big. So now I'm going to distribute, as you guys call FOIL, but let's talk about distributing. 20i times 5 is 100i. 20i times I is a 20i squared. 20 times 5 is 100. And then 20 times I is 20i. Again, I'm going to put my real component first, which is 100. Let's deal with the i's, which is 120i. And then I have this 20i squared. Again, we don't want any exponents greater than 1 for my i's, so this is 20 times 20 times negative 1, which is negative 20. Now if I can combine my real components, I get 100 minus 20, which is 80, plus 120i. And now it's in standard form. Now this problem is a little bit different. It's not to actually get you guys to combine like terms, because I don't actually have any common terms. If you think about these as being x to the 22nd, x to the 35th, and x to the 44th, I wouldn't be able to combine like terms because none of them are the same. But I want you to simplify this because this needs to be in standard form, or a plus bi. And I don't have any real components, and I don't have anything just to the I. So how do we do this? So what I'm going to do is use the fact that I squared is equal to -1 to help. That's the key. So this is 2 times, let me break this down to I squared. How many I squareds go into I to the 22nd? Well, 11. So if I have I squared, I squared, I squared, I squared, it takes 11 of them to get back to 22. Minus 4. How many I squareds go into 35? Well, it's not going to go in evenly, but if I have 17 of them, that gets me 34 I's, but I need one more to get to 35. Because 2 times, if you remember your properties for exponents, 2 times 17 is 34, but I need one more. Plus 10. If I have I squared, how many times does 2 go into 44? 22 times. So the reason we do this is because I know I squared is -1. And it's much easier to deal with real numbers than it is to deal with imaginary numbers. So I'm just going to substitute in my -1 everywhere I see an I squared. Now once I do that, I can just simplify. 2 times -1 to the 11th power. So if you remember negatives, if I have an even number of negatives, I get a positive. If I have an odd number of negatives, I get a negative. So this is -1 times itself 11 times, which is a -1. This is -1 times it 17 times, so I'm going to also get a -1 times the I. Plus 10, if I have -1 times itself 22 times, I'm going to actually get a +1. So here I get -2 plus, because I took 2 negatives, 4i plus 10. So again, we want my real components first, so this gives me 8 plus 4i. So that whole thing up here simplifies down to 8 plus 4i. So why we're going to talk about having I in the denominator, and why would that not be considered completely simplified? So if you remember, I is the square root of -1. So if I have something like 2 over 3i, why is that not okay? And technically it's all right, but we usually don't like this because this is the same thing as 2 over 3 times the square root of -1. And remember, we don't like square roots in our denominator, so we usually call it rationalizing the denominator. So how do we get rid of this? Well, if you remember when it was written in this form, we would just multiply our numerator and denominator by a -1. Okay? But we don't want to have to do all this converting. So what we're going to do instead is just multiply the numerator and denominator by I. This gives me a 2i in the numerator and a 3i squared in the denominator. But if you remember, I squared is just -1. So I'm going to get 2i over -3. And now I've rationalized the denominator. So we don't like to have any square roots in the denominator, and likewise we don't like to see any imaginary numbers in the denominator. So if you remember what we did in our last section, when we had something to look like 3 minus 2i, we multiplied by the conjugate to get rid of that radical. Okay, so the conjugate of 3 minus 2i is 3 plus 2i. And we're going to solve these, or simplify these the exact same way we did in our last section. So I'm going to distribute it in my numerator and get 15 plus 10i. In the denominator, if you remember, the reason we multiply by the conjugate is because our middle two terms simplify to 0. So we can just do 3 times 3, which is 9. -2i times +2i is -4i squared. But remember, the reason we do that is because that I squared is a -1. So what I have in the numerator is 15 plus 10i. It's in standard form. In the denominator, I have 9 plus 4, which is 13. So you could leave the answer like this, or a lot of times, since we want this in standard form, this is not standard form because I have real plus imaginary over real. What we would prefer you to write it as 15 divided by 3 plus 10 divided by 15 divided by 13 plus 10 over 13i. This is in standard form for a complex number, so this is the best answer to give. Okay, this is great that you got this, but to get full credit, you'd want to put it in standard form if that's what I ask. So what are these imaginary numbers and how do we graph them? We can graph them on the plane because when we graph imaginary numbers, we actually don't have just an x and a y axis. We have a real axis and we have an imaginary axis. So if I ask you to graph 6 plus 3i, remember this is our real component, our real number, and this is our imaginary component. So I'm going to go over 6 on the real and up 3 on the imaginary. So this is where point A would be. If I wanted to graph negative 8, 5, remember I'm going to go negative 8 on the real, up 5 on the imaginary. And this is where point B would be. If I wanted to go 1 minus 7i, this is my real, this is my imaginary, I'm going to go positive 1 on the real, down 7 on the imaginary, and this is where point C would be. And that's how we graph our complex numbers. But we have to graph it on what we call a complex plane, not a coordinate plane where it's x and y. Well, we also have the ability to find our absolute value. Sorry, I just wanted to resize that screen a little bit for you. So we can find the absolute value. If you remember when we did absolute value before, we were trying to find the distance away from 0. Well, we don't just have a 0 here. Now we're trying to find the distance away from the origin, which is in our case 0 for our plane. So how would we do that? Well, first we'd want to graph this point. So where would the point 7, negative 3 be? Well, I'd go 7 on the real, down 3 on the imaginary. So here, I want to know the distance away from our origin. Just like when we did a number line, we tried to find the distance away from 0. Well, if you remember a little bit from geometry, I'm looking for this. What is the distance from this point back to the origin? Well, hopefully you remember a little bit that that ends up just being the hypotenuse of this right triangle. So if I go over 7, okay, this is a distance of 3. I can do Pythagorean theorem, a squared plus b squared, okay, which is basically our negative 3 squared. Okay, we can square a negative 3 even though we went down. That gives me a positive equals our distance squared. Okay, I'll just put d for distance. So for this one, it's 49 plus 9 equals d squared. So we're going to get 58 equals our distance squared. So if I wanted to know the answer, and distance is always positive, it's the square root of 58. Okay, but 58, we should check to see if it can be simplified. 58 is 2 times 29. 29 is prime, so we don't get any pairs, so our answer would just be the square root of 58. Now what about negative 12 plus 4i? Okay, if my graph goes 10 by 10, it's too big to fit on here, but let's just do the same process. I went left 12 on the real, so that's negative 12 squared. And I don't have to worry about the positives and negatives because when you square something, it's always positive. And then I went up 4 on the imaginary, so I would get a triangle that looked like this, left and up. And I want to find the distance. So this is 144 plus 16 equals d squared. Okay, so my distance squared is just going to be equal to 160. But we want to take the square root of that. Let's get rid of my little picture here. If I take the square root of both sides, again, we want the positive, we're going to get the square root of 160. But I know that's 16 times 10, so my answer would be 4 root 10, and that would be the absolute value of a complex number. So hopefully now you feel a little bit better about writing a complex number in standard form, being able to simplify imaginary numbers, being able to rationalize the denominator with imaginary numbers, graphing a complex number in the complex plane,